I'm Ingrid Sheffer and this is Eddie Cliff. I'm the Vice President of the Australian Academy of Health and Medical Sciences and a child neurologist. And we're all very excited to see that you want to learn so much about a potential career as a clinician scientist. I'd like to start by acknowledging the Wurundjeri people as the traditional owners of the land and their elders past and present and their customs and culture. I hope we show you today there are many ways to skin a cat, or rather a mouse might be more appropriate experimental paradigm, by showing you can be a clinician scientist in a myriad of ways. You can be a physician or a paediatrician, but you can also be a surgeon, a public health researcher, an epidemiologist. You can be a clinician whose research is entirely basic science, so you change your whole persona when you go from the clinic to the laboratory. And we're going to have many world-leading experts showing you today about their science and their career and give you just a little taste of the many ways you can do this and show you how exciting it can be. This symposium is being is through the Australian Academy of Health and Medical Sciences. And just to give you a little background on that, this is a new scholarly academy that was launched in March 2015. And the idea is to really grow clinician scientists and to provide an authoritative voice for health and medical research in Australia. Fellows are Australia's leaders in health and clinical sciences and medical research, and we are all very dedicated to the cause and very keen for you all to think about a career as a clinician scientist. Eddie is a final year medical student at Monash, and I'll hand over to him.
And you might be wondering what a final year med student's up here doing next to an esteemed paediatric neurologist, but I actually have a bit more to do with this paediatric neurologist in that she's my mum. Now, Ingrid, or as otherwise known to me as Mum, was telling me about the academy and how the academy was forming, and I sort of was quite excited, and she was saying that she was chair of the Mentorship committee and they were running a mentorship program for associate professors and newly minted professors to really take them to the top of their fields in the world. And I was looking at the academy, and one of the mandates of the academy is to grow the next generation of clinician scientists. And I said to her, well, associate professors and professors are already sold. You don't need to, that's not the next generation. You need to go a bit younger. And that's where sort of today came about, was through that discussion. I said, well, how about we take the career of a clinician scientist, which I've been fortunate enough to see on an almost daily basis, both in terms of the highs and the lows. I get the full-on view, and that's sort of impressed me enough to interest me, so I hoped we could, through a range of vignettes, a range of really high-level examples, take that message out to you guys. So I also want to get a good idea of who's here. So put your hand up if you're a medical student. Imagine that's most of the room. How about if you're an intern or a resident? A smattering, probably most of them are. And how about registrar or fellow? Okay, also a smattering. And a PhD student? Okay, also a good showing. And consultant? I know there are a couple.
Oh no, there's more than a couple.
Okay.
So I would like to thank our sponsors, and particularly the universities. When I went to the deans of the medical faculties, Christina Mitchell, who is on the council of the academy, immediately was keen to sponsor it. The University of Melbourne dean, Mark Hargraves, was also very keen, as was Christine Bennett, who is the dean of Notre Dame. And I'd like to acknowledge their vision in realising we've got to get them young, and that's why we're all here today. I also would like to acknowledge the Club Melbourne Ambassador Program, and for those of you who don't know, Club Melbourne is led by the Melbourne Convention and Exhibition Centre for the support of the Melbourne Convention Bureau and the state government. And it works with sector experts to establish, secure and host international conferences that promote Victoria's expertise around the world and bring thought leaders to Victoria. So I'm a proud Club Melbourne ambassador, and we have over 100 now, and we have several of them speaking today, Professor Katie Allen and Professor Ewan Wallace. And something that they wanted us to bring to your attention was the recent launch of the Club Melbourne Fellowship. And this fellowship recognises excellence in research and leadership by mid-career Victorian researchers and supports the next generation of potential ambassadors. So the successful recipient of this program will get access to the Club Melbourne network for a year and receive research funding of $10,000. And you can find more information on all of this on their website.
So today we've got 4 sessions. The first session will be about why be a clinician scientist and what being a clinician sort of adds to your science. Then we'll look at what does a clinician scientist look like and have some examples of really outstanding clinician scientists from very diverse fields. Then after lunch we'll have some skills workshops looking at how to get yourself published, how to give a good talk, how to frame and structure a research question. And then we'll finish the day with a careers panel sort of titled The Best of Both Worlds. So that will give you an opportunity to ask lots of questions, although every speaker will have 10 minutes of questions, so we would really encourage you to ask lots of questions. You're also welcome to join the conversation or ask questions on Twitter. The hashtag's ClinSci. So we'd encourage you to get involved, whether it be through asking questions or on Twitter or both.
Okay, and I really wanted to emphasise that the speakers today are world leaders, so you're seeing the best of the best. Many, but not all, are fellows of the Academy, and everyone is giving their own time, and in the case of our next speaker, has travelled here on of his own choice and generosity to support this meeting. So thanks, Eddie, and we'll move on to introducing the first speaker, who is Professor Ian Fraser, AC, who should be known to everyone in the room. He really epitomises a clinician scientist, a leader and a visionary in the field of health and medical research. This is not least because of his seminal contribution to science as co-inventor of the HPV vaccine, which has helped to prevent cervical cancer around the world and has been recognised by the Prime Minister's Prize for Science in 2008, election to the Royal Society, and of course the Australian Academy of Science. But Ian brings also great leadership and vision, and for that he is the founding president of our Australian Academy of Health and Medical Science, and he's driven its mandate and its growing place in society and has come to us from Queensland today to speak with us. He is a role model for us all in that he encompasses generosity of spirit, and that is very important in a research domain, with vision and wisdom. And thus it's not surprising that he has recently been made chair of the Australian Medical Research Advisory Board, which is going to guide the Health Minister with how to disperse the Medical Research Future Fund. And that is hoped to add $2 billion to our research coffers by 2021, which is very exciting. Ian has also been recognised as Australian of the Year. So there are many different strengths and issues and approaches we can learn from Ian. So there's no one better really placed to tell us about why I became a clinician scientist. Ian.
Well, thank you, Ingrid, for that kind introduction. Normally, when you give a talk on an intellectual topic, you talk about, first of all, the what, and then the how, and then the why. I'm going to do it the other way around today, and I'm going to talk about the how I became a health and medical researcher, then perhaps why I became one and why I hope you might become one, and finally, how you should be a medical researcher, because I think that's the right order to do things. So how I became a medical researcher and is actually more to do with fortuitous circumstance than perhaps any specific intent. When I was a young schoolboy, I actually wanted to be an astrophysicist. I was really interested in what was at that time a very exciting era in astrophysics, because the technologies had been opened up that allowed us to understand a lot more about the universe than we had previously done, and every time you read in the newspapers about it, it was seen very exciting. So I obviously didn't pursue that line, and that was partly, again, a chance event. I ended up studying German at high school, and that was not because I wanted to study German at high school, but because I had a row with my parents. My parents were really keen that I should study history. I wanted to study music as a choice of subjects at school. They won out, but to annoy them, I then dropped French and decided I would study German. And how did that lead me to become a research scientist? Well, it's a complex story, but the first part of it was that because I was studying German at high school in Scotland, I was encouraged to go and get a summer job in Germany. So I went and took a summer job at the Porsche car factory in Zuffenhausen, near Stuttgart. My job was to test the correct preparation of the wheel bolts that held the wheels onto the car. So if you've got a 1971 Porsche, I would be very careful about how you drive it around corners, because I don't guarantee that the wheel bolts will hold the wheels on. But at any rate, I stayed with my German pen friend, and he had a girlfriend across the other side of town. Now, his parents wouldn't let him go and see his girlfriend unless I went along with him. I don't know, I was supposed to be a chaperone for the mail. It was a little unusual. But at any rate, I would go there, but of course I was as wanted in that particular engagement, as you might imagine. So I was kicked out once we got to see the girlfriend. And since I didn't know anybody else, I actually went and talked with the girlfriend's father. Now, he was a clinician scientist, Professor Guntert from Tübingen University, and I was still thinking astrophysics, and he was saying, yeah, look, astrophysics, fine, but there's no jobs there. I think you should go into medicine. So I did. Well, as you do, I came back to Scotland, and instead of studying physics at Edinburgh University, I studied medicine. And then, because I studied medicine, and because I was interested in science, I wanted to do a little bit of research, and I started doing research as a pathologist in the pathology department there, and realized that all the good immunology which I was studying was being done at the Walter and Eliza Hall Institute in Melbourne. So that I decided that I had better come out to Melbourne when I got the opportunity and to see if I could get some sort of job here. And as an undergraduate student, I came out and visited, and then I went back to Scotland again. One big advantage, by the way, of changing to medicine rather than physics was that I actually met my wife that way. The physics crowd were very nerdy, and they didn't go into that sort of thing very much. The medical crowd were a much better social crowd, and you got a better opportunity to meet people, shall we say. Anyway, I came out as an undergraduate student to Melbourne, worked at the Walter and Eliza Hall Institute for a short while, went back to Scotland, and realised that if I was going to make a career in medical research, then it would probably be quite important that I went to the best place in the world. So that's a message I hope that you understand. You would really want to be in the best place in the world if you're going to get a training. So I decided I would come back to Australia, had to then apply to emigrate here, and they asked me if I had a criminal record, and I said I didn't realise you still had to have one to come here. But they let me in nonetheless. And I worked in Ian Mackay's lab at the Walter and Eliza Hall Institute. At that time, he was studying liver disease, and I ended up studying liver disease as well. So he suggested that I should go off to Europe to meet with the experts in the field, because that was traditional in those days. You went to Europe if you could from Australia. And because I spoke German, because I'd learned German at school, I decided I should go to Germany, because I could at least converse with the scientists there. And he wanted me to go and see a guy called Hans Myers from Buchenfelde, who was the expert in liver disease at that time. And so I went to see Hans Myers from Buchenfelde at the German Cancer Research Institute. And Hans Myers from Buchenfelde was a very senior German, very proper German. And he took me to introduce me to his boss. And his boss happened to be Harold Serhausen, who at that time ran the German Cancer Research Institute. And Harold said, look, you don't want to study liver disease. Liver disease is boring. I'm interested in viruses that cause cancer. And why don't you get interested in that area? So I thought, okay. When I went back to Australia. I was getting a bit fed up with working with liver anyway. I don't know, working with liver is sort of messy stuff, and you don't like eating it, well, you don't like working with it either. So I decided I would change to work on papillomavirus. That, of course, has led to some very interesting research for me. It also then meant that I had to learn from people who worked on papillomavirus. So I made another trip across to Europe, this time to Cambridge University, where I met Margaret Stanley, who was at that time the person that was working most on papillomavirus. And there I had the good fortune to meet up with my erstwhile colleague, Dr. Jan Zhu. Now, Jan and I had two things in common. One, we were both absolutely fascinated with the idea of papillomaviruses and cancer, but much more importantly, neither of us spoke English. He spoke Chinese and I spoke Scottish. And so in the lab, we were the only two people that were sort of ostracized, and we sat in a corner and talked with each other about papillomaviruses. And that led, of course, to me getting Jan to come out here, and in due course to the development of the vaccine that we now recognize that protects us against cervical cancer. So that was my journey to here and to where I got to. And as you can see, it wasn't exactly preordained that I would end up there, but if I had stayed studying French, I probably would have stayed studying physics, and therefore I would have probably ended up as a broke astrophysicist working somewhere in France rather than a comfortably off clinician scientist working in Australia. So that's how I got there. Now, thinking a little bit about why we do it. If this thing works. No, probably not. Does it need to be switched on? Aha. Well, that's the first lesson that you learn as a scientist. Get somebody who knows what they're doing to work the equipment for you. Okay. Well, why would you want to become a medical researcher? Well, hopefully it's because you're driven by curiosity, because good science starts with a question that you really want to get an answer to. And if you're interested in health and disease, and I could gather most of your medical students, then you should be really interested not only in the delivery of the service, which is very important, but also in the problems that you're trying to solve. And curiosity starts early. This is me in Scotland, and when I was about 3 years old, taking my tricycle to bits. If you have the urge to curiosity, build on it, because that will be what will drive you in the direction you want to go. A second equally important reason is because you want to make sure if you're doing things to patients, and you will do things to patients, that you get it right. And tradition is not a great basis for getting correct treatments. We have, we would still be using leeches if we did things traditionally. Actually, we do use leeches still, by the way, but just for a very limited scope of work. So the reason that we can get it right is because we do research, and that really means that every single person who is working in health and medical service delivery should be doing research, at least at the level that they understand what the research is about, what the research methods are, and how you can apply them. Because if you don't have that, you can't actually contribute to the discipline that you're working in. I started in medical research at a very early age. One of those three individuals up there is me, and I can tell you that I haven't changed my sex or my skin color, so you should be able to work out which one it is. But when I was an undergraduate, my job was to put the infusion lines into patients that were going for surgery, and since my job was then to replace them when they clotted up, I used to get really fed up of being called in the middle of the night to replace a line in somebody's arm after they'd had surgery. And I really wondered if there was a way of reducing the risk of that happening. So we did a little project looking at the different means by which you could put intravenous lines into patients. And because it was an interesting little project, we thought we should write it up, and it got published in the British Medical Journal, which was my first research paper. So you're never too young to start doing the research. If you're curious, if there's a question that needs an answer, just get out there and answer it. So at the end of the day, you do the whole thing because we're all in the same game of trying to look after society better through the medical care that we provide. And I think that I've had the good fortune to choose a significant problem to deal with because I was really interested in viruses that cause cancer as a result of my interaction with Harold Sirhausen, who described how papillomavirus was responsible for cervical cancer. And so it's good to choose a significant problem. Ingrowing toenails does not fascinate the community nearly so much as cancer, and you should pick an area where you think you can make a difference because you think it's important. Of course, it does help if you become part of the solution to the problem, And I've been very fortunate to be part of this solution because Harold Zerhausen's work enabled the work on cervical cancer, and Janzu and I came up with the technology which eventually led to the vaccines. And I should acknowledge Andrew Cuthbertson and CSL because they were a key part of this process of getting from the technology that we developed in 1990 to the vaccine. So they're now out there in since 2005. But the important thing is choose a problem that really excites you, that's worthwhile answering. Do not choose a career in medical research because you want a secure career. You have to get used to a funding model which is not likely to change in my lifetime unless you can come up with a solution better than the ones that we've come up with. You have to get used to 3 to 5 year funding. But one of the advantages of being a researcher in health and medical research is that you have a fallback position, that you can just go on being a professional in your area and helping other people to do research. And I think it's important to remember that. But I have to say that amongst all the people that I've mentored over 40 years now, every single one of them who wanted to get there has. You know, if you're determined, you will contribute to the field. And don't do it for money or fame, although quite a few of my students have maintained that that was the reason they went into it. You may get there, you may be lucky, like I was, and get both the fame and, well, at least a gold medal, if not the money. But it's not a good reason for doing it of itself, because most of you, if you do health and medical research, will be putting one piece of the jigsaw puzzle in, and that's the satisfaction you get. You may not be putting the last piece in, but you will be putting a piece into the puzzle. And without all the pieces, you don't have a solution to the puzzle. And if you're lucky enough to put the last piece in, or a key piece, or maybe an edge or a corner somewhere, then you may get a little more acknowledgement. But you'll always have the satisfaction you've learned and done something useful. Okay, so I've sold the idea. Now, how are you going to go about doing it? Okay, well, you have to be ready for the rough and the smooth. This is me again in Scotland, the one sunny day in Glasgow that we could get a photograph. Note, impoverished scientist, no money, tin bath. There's at least a smile on the face. Don't expect it will stay that way all the time. Times get rough and you will have to accept that there will be bad times as well as good. 98% of your science will not work the way that you think it will. And you just have to acknowledge that's the way it goes. You have to define success in different ways. In other words, success is not necessarily getting it right all the time. Success is knowing you've contributed usefully to the field. You might get a university named after you, the University of Ian. Well, not really, but that's what they said. Or you might get a title like that put up about you, which I think it was actually the vaccine they were talking about there, but never mind. And it may not always turn out as you expect, because that was what Cosmopolitan magazine had to say about me. Oh, well, you take the rough with the smooth, but you would aim to be the one that puts the last piece in the puzzle. You probably will just have to be content with putting a piece in. Okay, so how are you going to go about making sure that you get to the right place? Just make sure I'm not using all my time up. So first thing is, you really want to choose a mentor or two that you would aspire to be like. And then you have to choose a problem. And I was fortunate, and I had a number of mentors. I had a very good clinician when I was an undergraduate student called John Monroe, who I don't have a photograph of, unfortunately, who taught me how to be a good clinician. And he inspired me to do research as an undergraduate and as his resident and eventually as his registrar. He had a very clear vision that you treat the treatable. This was his philosophy in medicine. You don't worry about things you can't do, but if you can do research to try and solve the problem, you should do it. And then I came to Australia, and this is a very young Ian Mackay, who was my mentor in Australia. And he taught me that you should focus on the patient all the time, because that's really what drives the agenda. And then this guy, Gus Nossel, who's known to you, I'm sure, taught me another very important thing about science, and that is communication is a great part of it. You have to be prepared to go and sell what you're doing. You start by selling it to get the money to do it, by selling it to get somebody to supervise you to do it. Eventually, you end up having to convince the community that what you're doing is a good idea, and government that it's a good idea. So that being able to project your vision for what you're wanting to do to the world at large is really important. And if you're choosing a problem, well, genital warts, which is where I started, probably isn't the most exciting thing, but it was better than liver disease. I started with, I've worked my way through every sexually transmitted infection you can think of: hepatitis B, hepatitis C, HIV, AIDS, papillomavirus, now herpes. So there are plenty of problems out there to solve. But just remember, you might have to talk about it over dinner with your partner, so you might want to choose something that's not too difficult to discuss in public. Second step, you've decided on your mentors, you've decided what you want to study. You have to become the expert in what's been done in the past in your area. It's not so difficult these days because you have at your disposal all sorts of electronic tools that were simply not available when I was a medical student. When I had to go to the library to learn about something, there was a thing called Index Medicus, which occupied about half of all the library space. And it went back to 1843, was volume 1. And if you wanted to find all the papers in a particular area, you literally waded through all the volumes, looking under whatever indexing term you could think of to find out. But you do need to know the area as best you can. This guy, Rigoni Stern, was the one who did the epidemiology of cervical cancer, and I'll come back to that in a little moment. But the history of papillomavirus and cervical cancer started with a guy whose job was to try and prevent cervical cancer, and he came up with the idea of screening for it, the very first screening test for a disease. And he invented the PAP test, which at that time was screening not for preventing cervical cancer, but actually catching it early so it could be treated. And then, of course, Harold Zerhausen drew the link between the virus and the cancer. The guy, Rigoni Stern, was really quite interesting. He was a mathematician, and there's another lesson in that, and that is that you should be quite prepared to cross disciplines to get answers to your solutions. He was interested in who got cancer, because remember in 1840 when this was being looked at, the understanding of cancer as a disease had really just crystallized out. You know, the concept that cancer was a growth, something went wrong with tissue, that became possible because people developed histological techniques, which I'd remind you grew out of the dye industry in Germany. There was the people who dyed cloths that came up with the stains that enabled us to look at sections of tissue and work out that there was actually something wrong with cells in there. So that Rigoni Stern was a mathematician, and he was aware of the fact that the cancers that were common in those days, and remember in 1840 the average life expectancy was 40 years. So in Italy in 1840 there were only 2 cancers to worry about. They were both cancers of women. One was breast cancer and the other was cervical cancer. They were the 2 cancers that occurred in people under the age of 40. And he made a correct observation that nuns were much more likely than what he called other women to get some cancers, and particularly cancer of the uterus was commoner in the other woman, and cancer of the breast was commoner in nuns. Just to put that in perspective, in 1840 in Italy, about 1 in 5 women was a nun. If you couldn't marry off your daughters, you sent them to the nunnery, because that was the only way that they would get a living. So that there was a fairly large number of nuns to survey. And so he drew this conclusion, which was a correct observation. And then he put up a hypothesis. And now this is where you've got to be careful not to cross disciplines, because mathematicians should not hypothesize easily about the cause of disease. So he thought that uterine cancer was not increased through the licentious practices of women, but rather it was greatest amongst women who were excessively sensitive, morally, and nervously irritable. Not quite sure what the definition of those terms would be when you were doing the epidemiological survey. He didn't do much better with the breast cancer. He thought that breast cancer might be due to the fact that the nuns' habits were too tight and they crossed their hands across their chest, and that would compress the breasts and cause breast cancer. So dangerous thing, putting up hypotheses. You might have to test them. Interesting thing, that's a testable hypothesis, that one. The previous one is not. I do not know that you could make a control group of nervously irritable women to test a hypothesis. But this one you could if you really wanted to. You could go out there and test it. And that's important to remember. If you have a hypothesis, you have to have a test that you can apply to see if your hypothesis is correct. In other words, research is based on observation with the idea that it's falsifiable. In other words, it must either be true or not true, and you must be able to tell. Anyway, having got through the process of working out what area you're going to work on, picking a problem, getting some sort of idea about what the history of the problem is, you then have to get a good technical training. First of all, a training in research methodology, and that starts right now. You know, you're never too soon to start doing that. Expose yourself to the science, go to the talks in the hospital, go read the journals, read the newspapers, find out what's going on there. And then hopefully if you get on with your research, you'll be writing plenty and publishing papers, and that will give you the chance to interact with other people who are doing the same sort of thing, who want to know what you're doing. Very important, learn ethical scientific behavior. There are many dimensions of ethics. Now, I'm not going to talk about them all today, but it really is important to understand that this is a discipline where you are the policeman of your own work. You are responsible for making sure that the science you do is acceptable to the community, is actually correct, and to the best of your ability done in a way that will allow other people to draw conclusions from it. And that's what ethical scientific behavior is about. You will learn that from your supervisor, you will learn it from the other people round about you, but it's ultimately you that determines whether you get that right. And if things aren't working out, if you've gotten to the wrong place with the wrong supervisor, change. Don't wait and see what will happen. I see so many careers wasted because people decide that they should stay loyally with somebody and it's not the right thing for them to do. So be prepared to change if you have to. You've got to work out what your career is going to look like, and now is a good time to start planning it. Work out what you'll have to do for the progression from one stage of it to the next. That's one of the things the Academy of Health and Medical Sciences is trying to do for clinician scientists, but whatever area of research you end up in, it's really important. You'll do good work because that will be the driver. You'll first of all have to demonstrate you can do it independently, because that will be the proof that you can really look after yourself in science. But then you will have to do it working with others, because research is a team business, and you really have to show that you can work in teams and deliver more effectively by doing that. Eventually, you will start supervising others who are doing science, and you'll have to then work out the balance of how you look after their career and their science versus your career and your science. You're going to have to spend a lot of time learning how to con people into giving you money. There are many ways of doing that. Legal ones are preferable. I wouldn't go for the other ones, but learning to write grants is important, learning to collaborate is important, and also participating in the whole process of looking after your colleagues through peer review, because the whole system will either be run by us, for us, or it will be run by someone else for us. And by and large, if it's a choice between us and someone else, I would go with us any time. So it's important not to let it get out of our control. And eventually, you'll have to decide what you're good at. That might be a technology, it might be an area of interest, it might just be that you're the best science writer there ever was. You know, you're going to have to pick an area and be in the hopes that you will then make a career out of it. I was very lucky to meet this guy. Partners are really important in science. This is Jiangsu in Westlake in China. He was kind enough to take me around his home university there. And his wife was a major driver behind this. I mean, well, he was talking about things, she did all the work. And that's absolutely true. All the science that came out of that collaboration was done by Xiaoyi. But you will build teams and work with people. This is my team from about 10 years ago. I recognize a few faces in there still. Over my lifetime, I now have a contact of about 120 people that I have mentored through a science career. And they are great because I can go and visit them anywhere in the world anytime, and they're always pleased to see me. At least I think they are. They always say they are. So aim for your group to be the world leader in its field, because there's no point in being in science unless you're doing world-leading science. That sounds very hard, but Me Too science doesn't help anybody. It's the groundbreaking stuff that makes a difference. And you've got to learn this business of giving to your next generation, look after them. And you've got to learn to promote science in the community. But the other side of things, by the way, is you've got to make sure you have a life outside of your health and medical research work, because it is a very challenging business, and you will get, I'm sure, mentally exhausted from time to time. And so make sure you've got something else to do. This is me with my son skiing in the States. And that's, interestingly, all three of my kids said they were not going to be a medical scientist like their dad. One studied law, one studied engineering, one studied veterinary medicine. All three of them are now doctors, and all three of them are, well, two of the three of them are doing medical research. So it just goes to show that you can still act as a role model, even if they didn't like the role model very much when they first saw it. So we'll probably start to wind this up a little bit and let you ask some questions. But I'll just set you a couple of challenges, because this is what it's all about for the future. When these cartoons were drawn at Temple Wall in Komombo in Egypt some 5,000 years ago, this is a birthing stool, and these rather interesting looking instruments that look like they're for building the temple are actually means of getting bladder stones out of the bladder, because schistosomiasis was a dominant infection in Egypt, and bladder stones from schistosomiasis were extremely common, and these things were helped you to hook the stones out. Anyway, when these cartoons were drawn on the temple there, the average life expectancy in Egypt was 40 years. The average life expectancy in sub-Saharan Africa is still 40 years. We haven't managed to improve it over 5,000 years of practice. But on a global basis, it stayed at 40 years until the 1840s. You know, all of the nostrums and things that we did for people up until the 1840s made no difference to life expectancy on the planet at all. What made a difference were two revolutions, and it wasn't the American and the French one, although they both occurred just about that time. It was the agricultural revolution, which gave us plenty food, and the industrial revolution, which gave us safe water for the first time. And the reason that Africa still has a life expectancy of 40 years, sub-Saharan Africa, is because they still do not have access to safe water and enough food. What's happened, of course, since then is vaccines and antibiotics in the 20th century, which have added 15 years by getting rid of most of the childhood infections that used to wipe out large numbers of people and bring the average age of death down considerably. Of course, some of this is going to be lost in the 21st century. Your generation are going to have the challenge of the post-antibiotic era to deal with, and I think it'll be quite an interesting one, if that's the right word for it. And all the rest of research has only added a very few years up at the top there to life expectancy. But of course, that's to miss the point, really, isn't it? Because the medical research that we do nowadays is not so much about prolonging life, but increasing the quality of life and dealing with the chronic diseases of aging, which I will no doubt get in due course, and which I hope you will have solved before I get them, because that's really where the challenges are. And this is the last one that I'll leave you with, and we can't ignore it, and that is that since 1960, GDP has grown in Australia at about 6% per annum. Expenditure on healthcare has grown at about 9% per annum and is still growing at that rate. And this is a global phenomenon. We are spending more and more of the wealth that we produce on healthcare. And that is not a sustainable exercise. So that research is a fundamental part of the solution to this problem. The research can do two things. It can make us use our money more effectively by getting rid of a bit. This is one of these awful graphs that economists put up, but basically this is looking to see what the benefit you get from dollars spent is up this way and the actual dollars that you spend. And so vaccines and public information systems come cheap and give good health outcomes. At the other end of the spectrum, adverse drug reactions and preventable surgical complications actually make us worse but cost more money. So that basically this is a diagram from the McKeon Committee report, which if you have time you should, well, I don't know, don't read the report. It's a very thick volume. Don't even read the summary of the report, but you could perhaps read the summary of the summary, which is only 2 pages long, and it tells you what we thought should be done in health and medical research. The point is that although that's important, we actually don't live in an economy, we live in a society, and remembering that medical research is about improving the wealth of society. The wealth is not so much financial wealth as social capital. That's what we get out of medical research. But you can't forget that graph where we're spending more and more on healthcare, because governments never will. They have to live with that. So those are the challenges that you face when you go into medical research. You've got to solve the practical problem that we're spending more and more on healthcare at the same time as you make us live longer and healthier. And that will be your challenge for the 21st century. And I'll stop at that point. Thank you very much for your attention.
Well, thanks, Ian. I hope you heard there were so many pearls in every slide there and really messages that you should think about in your career as you think about what you're going to do, but also about the worth of what you're going to do. Now, we're fortunate that we now have 15 minutes or so that Ian will take questions and comments. And we have some roving microphone people, so please put up your hands and let's take the opportunity.
If they don't, I'll throw some out to them.
That's a great idea.
Yeah, if you don't ask questions, I'll ask questions of you.
My question is, what should you do when the professors never reply your emails or don't seem to be on board with you?
Well, as a guilty professor, I would have to say that the best thing is not to send an email, but to go see the person or phone them up. Email is a terrible, I mean, look, email is the curse of the 21st century. If we could have put the genie back in the bottle and not invented email, I would do so like a shot. It gave me 1 year of real use, and that was when it started and I could start to communicate with my colleagues overseas in health and medical research quickly in the days when up till then the journals had come by post and took 3 months to get here. And that was in 1991. And then after that, I just wish it had never been invented. The first thing that should go is the ability to attach any document onto an email, by the way, because that just makes it impossible. You know, just read this by Monday and let us know what you think. No, forget it. Personal contact is really important. If you think your case is a valid one, whatever it is you're wanting to go and talk about, make sure you actually go and if you can't do it face-to-face, at least phone them up. And acknowledge that they're probably busier than you are, which is probably going to be true, and therefore don't expect them to drop everything like that and get in touch. And if you must send an email or a letter, make it short and say what you want and how you think that they can help. This is just communication skills. Social media 101. Do not Twitter what you want, and preferably not on Facebook either. Instagram's all right if you send nice pictures. I have an Instagram presence, but I do not have a Twitter presence, although I have a Twitter handle. Communication is one of the challenges of the 21st century. Keep it direct, keep it personal.
Great question. Can we have some more? Yeah, over here, Elaine.
Professor Fraser, thank you very much for giving us your time today. I wanted to ask, what stage in your career did you change from liver disease to viruses?
It was pretty much during that visit to Harold Sirhausen in Germany. Look, I was working on, Ian Mackay was a clinical immunologist who was interested in autoimmune disease. And what he wanted me to do is to work out how the immune system could damage the liver to create a disease called chronic active hepatitis, which in those days was partly autoimmune and partly due to viruses. And I had come to the conclusion that while the question was a very interesting one, the technology to answer it did not exist. First of all, there was no animal model of the disease, so we couldn't do the non-standard dissection that you would do in an animal model to work out what was going on. And secondly, the technology for looking at anything in the way of an immune response in a human other than antibody was just not there. And while antibodies were a part of the autoimmunity in chronic active hepatitis, they were clearly not the cause of the disease. So there wasn't an obvious path forward. So I was kind of looking around for something different to do when I went to see Hans Meyerson Buchenfelde, and I just saw this great opportunity in a virus that caused cancer, because what I was really interested in at that time, and what I was driving my interest, was how it was that some of us get infections and clear them off without getting any problems, sometimes without even knowing that we have them. And others get an infection and it makes them sick, or even goes on to cause a chronic disease. In other words, your immune system and my immune system do not handle the same challenge equally. And I really didn't understand the basis of that, and I didn't think anybody else did, but it was clearly an important issue, because if you could get rid of these chronic infections from the 10% of people, I mean, I was particularly interested in hepatitis B at that time, because I had been the renal registrar in Edinburgh at the time that hepatitis B went through and killed several of my colleagues, because we had an epidemic of chronic hepatitis B infection in the renal unit. bloodborne disease. Renal units are blood everywhere. At least they were then. I think they're a bit better now. But so I was looking for an area that I could get into which more addressed my interest at that time rather than my boss's interest. And Harold Sirhausen gave me the opportunity. He said, here's a virus that causes cancer. Can't get rid of it. Now, why is that? It's a virus. The immune system should fight it. And that's why I changed area.
May I just clarify, was this during your PhD and then postdoc or before?
It was during a postdoc.
During a postdoc.
Yeah.
So it's about the right question at the right time with the right team.
Yeah.
So can we have some more questions? Oh, behind there. Helena, over there.
Hello, Prof. Thank you for speaking. I just wanted to ask, in one of your slides, you mentioned changing your supervisor or your project, or even the place you're working at. Now, that can be a bit difficult to get across sometimes. It's a bit like, I'm breaking up with you. I'm sorry, this is not working out.
Yeah, absolutely.
And you've definitely done the change. So any advice on how to do it in a gentle way or that won't offend anyone?
As with personal relationships, it's usually pretty obvious to both partners that it's not working out when it's not working out. You may think that you're uncomfortable and that your boss is quite comfortable with how things are going. Chances are he or she is equally uncomfortable for whatever reason. It may simply be that the project isn't one that's tractable at that time, or it may be that the areas of interest of your boss and you just don't overlap. But the point is that, again, as usual, if you go and talk about these things, and first of all, you don't wait until it becomes an absolutely crisis point problem. Free communication is allowed. You're allowed to talk to people. Of course, there's a dependency relationship there, and that makes it a little difficult. It's much more parent-child than it is partner-to-partner. But it shouldn't be. It should be a partner-to-partner relationship because you're both in there for the same reason. So the important thing is, first of all, if you are working with somebody and they're technically your boss, get the relationship right as early as you can. When I get new students into the lab, first thing I do is they come round for a barbecue with me and my wife, just the two of us and the student. So I get to know them a bit socially. And then we always have regular lab barbecues where everybody gets together so that there's a good social relationship established with somebody before any problem becomes apparent. And that makes it much easier to address the problem when it actually happens. If you've got to the situation that there is a problem and you haven't got that social relationship, recruit a third party to help you. Every student, every postdoc should have a mentor anyway, and you should be using them. And it's the sort of thing you would talk with them about. They can even act as a go-between. Don't expect them to solve your problems for you. Mentorship is not about being the solution to the problem. It's to help you solve your problems. But they can suggest strategies, and they can also talk with the other person and see if they feel the same way. So, it's usually a tractable situation. Occasionally it becomes really adversarial. And in that case, you really need to get a third party to give you a hand, because otherwise both of you will get hurt.
I think with a PhD too, you often have a period where you're not so enamoured with your mentor, with your supervisor, and that's sort of, the PhD is a long road, very exciting road at the end, but it has its periods of, what am I doing? Bit boring. Oh my gosh, panic. And then finally you look back and you say, hey, that was worthwhile. So I think you've got to know that that's also part of that journey. Would you agree with that? Is that too strong?
Yeah, by and large, that's true. As I said, 98% of what you do in science doesn't work.
You've got to remember that, 98%.
And that's the really frustrating bit. And you will get frustrated. But the frustration should drive you forward and start you thinking laterally. It shouldn't become a big sword that hangs over your head. So if it's getting to the sword over the head business, that's when you've got to start talking. If it's just frustration, look, I could do this better. It should be driving you back to think of new ways of doing things. And when it becomes destructive, that's when you have to start recruiting other mechanisms to sort the problems out.
More questions? Middle here.
Hi, Professor Fraser. Thank you so much for speaking to us.
Elena, run along, and yeah, it's much better with the audio. And also we're recording this, so it's better from that point of view.
Thank you for speaking to us, Professor Fraser. I have two questions. The first one is, could you tell us a little bit about current and imminent advances in vaccine technologies? And the second question is regarding your role in advising policymakers. Have you found that over the years you've become better at engaging with their concerns, and that argument you bring up about medical research leading to wealth and social capital, how persuasive is that with policymakers?
Right, well, I'll tackle the second question first, because the first one is basically a science question. I could spend 20 minutes talking on that. Look, we have to engage with our politicians. They are our leaders, our chosen leaders, and they are the ones that control the funds by and large, our funds, our taxpayer money, but it's them that tell us how to use it. And we elected them to do that, and so they should do it. I mean, you know, if they were they are the board of the company in which we are shareholders, and shareholders elect a board to run the company effectively, so we should let them do it. They should, of course, seek advice, as all people would if they're making difficult decisions. But the interesting thing from the point of view of the politicians is that they know what the problems are, and there's no point in me going saying, look, we want more money for medical research. They know we want more money for medical research. They would love to give us more if they had it. What we have to do is to make solutions for them and say, look, this is what we can do better, and think about how we can work with them to try and solve the problems that they have, that we have. So, I mean, look, some politicians like us, anybody, you can always find really difficult characters that are not going to be out there to help you, but the majority of people who are politicians get there because they actually want to do something useful. The system corrupts them eventually, and don't quote me on that, but it tends to make them more interested in their own survival than it does in the problems that they're trying to solve. But that also is understandable. If we gave them 10-year terms, they might be a little more amenable to thinking about 10-year solutions rather than 2-year solutions, which are hard to get. So I think the important thing, again, as with everything, is talk to people. I mean, I talked my way into getting a $350 million building for health and medical research built in Queensland. It took me 6 years to do it, and it involved going on a cycle ride with Tony Abbott at one point from Brisbane to Sydney. But you know, there are ways and means of getting to talk to people if you really have to. And usually, if you've got a good story and a convincing argument, they'll listen. And the convincing argument, I think, was that we needed a facility which was more focused on getting the translation of research into the clinic than many of the research institutes had been at that time. So that if you've got a good sales pitch, you'll get there. As for vaccine development, yeah, right, okay, vaccines 101, the easy vaccines are the ones we have already. The really hard ones are all the other ones. And vaccine 201, the easy vaccines are the ones where we can make an antibody and the antibody neutralizes the infection, and the hard ones are where it doesn't. And there we need new technologies, and there's a lot of people out there developing new technologies, but we still don't have a really good vaccine that will prevent or cure an infection where antibody won't do the job. So there's your challenge. I know what I think the solutions are, but you've got to go and find some too.
Well, one more question there.
Thank you, Prof. Fraser. I'm just interested, you trained as a clinical immunologist. How much clinical work have you done over your career?
When I first graduated, I was full-time clinician for the first 5 years. I mean, that doesn't mean I wasn't doing research. I was publishing papers, but I was working full-time as a clinician. The people that paid me expected me to provide 100% clinical service. When I came to Australia in 1991, 85, have to think about that a bit. I took a job which was 50% clinical, 50% research. And basically that carried on right the way through until about 2002, when I decided that the clinicians knew an awful lot more about things in the areas that I didn't know about than I had ever known. And particularly, I found that I was relying more and more on my more junior colleagues to keep me up to date in areas of medicine which I wasn't up to date in, and I realized that the safest thing to do at that time was to effectively retire from clinical work. It's very difficult to be absolutely top-notch across the whole area of medicine at the same time as you're leading a research team and running a research institute. And it's a hard decision to make that, but As a clinical immunologist, I had to be able to cope with anything that came in the door. And it was easy to be up to date in clinical immunology, but really hard to be up to date in cardiology, neurology, and respiratory medicine. And those areas were just as important for the patients as the clinical immunology problem that they told me about. So I've just decided it was better to get out at that point.
Well, please join with me in thanking Ian for an absolutely wonderful talk. Ian will be with us over morning tea, should you want to have a chat with him before he heads back late morning to Queensland.
So now I have a quite unique and very great privilege. Mum is a paediatric neurologist and a professor of paediatric neurology research at the University of Melbourne and director of paediatrics at Austin Health. She works in epilepsy genetics, in epilepsy classification, in speech, in autism, with a big team, a very multidisciplinary team, and her closest collaborator, Professor Sam Berkovic, who you probably don't realise was her PhD supervisor once a time, and now they're co-lab heads. Epilepsy genetics was a field that didn't exist when Mum was doing her fellowship in the UK, and when she told her mentor in the UK that she was coming back to study epilepsy genetics, he laughed at her. Unfortunately, 10 years, 15 years later, he sent an email saying that he was wrong and that, yes, epilepsy, a lot of epilepsy, did have a genetic etiology. Epilepsy classification, the way I usually explain it to my friends is you probably have heard of the DSM when you went through medical school, or which is the diagnostic manual for psychiatry. Well, what Mum worked on at an international level was the equivalent for epilepsy. And you'll hear a little bit about some of those things, hopefully. So I'm very proud of her, and I hope, I'm very glad that you'll get to hear some of her stories. Without further ado, here she is.
Thanks very much, Eddie. It's quite a privilege to be introduced by one's offspring, so it's pretty exciting for me too. So Eddie and I thought that I should talk to you really about clinical science, because that's what I do. And in some ways it's an undervalued gig, I think. I think that people don't realise how much you have to be a clinician to do clinical science. And it took me 21 years from completing medical school to handing in my PhD. I gave birth to two boys. As you can see, one turned out pretty well, and so did the other. But anyway, really taking you now with your clinical skills that you're getting and showing you how you can take what we do as clinicians, clinical observation, and taking that further, drill deeper and make a difference. So what we do, and we all do this now as clinicians, is sit in the clinic, see a patient, and that is many of us are doctors here or medical students, but there are also allied health professionals. You also do this. You see the patients in the clinic and you say, what's special about this patient that they're telling me that is different, that is telling me about the biology? And you'll hear in the vignettes I'm going to share with you that we look towards etiology, but then one needs to take it further, and one can't do that alone. One needs a great team, and I'm really fortunate to work with a fabulous team of physiologists and basic scientists, as well as imaging people, psychologists, all sorts of specialists that help me to drill down and understand the mechanisms of what's going on for my patients. But then it's back to us again, because we have to translate that back to our patients. Partly education, as Ian was talking about, and communication about science, but very excitingly, and this is going to be in your time, translating the science back to making a difference to the outcomes of their disease. And we've already heard about that with that longevity curve, but there's still much to be done. So in my talk, we're going to give you two major stories about clinical research. The first was the first gene for epilepsy, but I'm going to take that from when we first found that in 95, fast forward to 2016, and show you how this science, this clinical science, married with molecular science, is now helping us to get to precision medicine. I'm then going to speak about the vaccination story. I'm sure a few people in the room will have heard that, but it was a very important observation that Sam and I made about how vaccination wasn't causing disease, and this is still a huge problem in our society, as shown in our recent election. And I think Ian did the story about why become a clinician scientist superbly. I have just a couple of slides at the end that are touching on some of the same themes, but I think all the speakers today will give you those themes. So just pick them out of what they're saying about answering important questions and those sorts of issues. So Epilepsy 101, I hope everyone in the room knows this, but 4% of the population has epilepsy at some time in their lives. And if you add in febrile convulsions, also known as febrile seizures, that's in 3% of Australian children. And seizures are due to abnormal electrical activity in the brain, and we picked this up on the EEG. There are many, many types of seizures, and most of epilepsy begins in childhood or adolescence, which is why it's so important in child neurology. And when I see a patient, I try to diagnose them according to a specific epilepsy syndrome. And that is one of the reasons I've been so involved with epilepsy classification, because that is around syndromology. So the epilepsies are broadly broken down into two major groups: the generalised epilepsies, which come from bilateral involvement of corticothalamic circuits in the brain. And we know that they're genetic, but how do we know that? Clinical research, not because we have the genes for most of the patients. And here you see identical triplets that all have juvenile myoclonic epilepsy. So that tells you very clearly it's a genetic disease. The second major group are the focal epilepsies, and the focal epilepsies, of course, are where the seizures begin in one part of the brain. And these were always considered acquired diseases. And when we talk acquired, we're talking about people thought always a structural abnormality of the brain, such as the one shown here, hippocampal sclerosis, where you have scarring of the mesial part of a temporal lobe. And that's the most common finding in uncontrolled temporal lobe epilepsy. So that was the point at which I entered this area in my PhD studies, when people just didn't think epilepsy was very genetic, and focal epilepsy is 60% of epilepsy. So it starts really with the disorder that this man has, and here you're going to see two different seizures in a 40-year-old man. And what I want you to observe is just how highly stereotyped they are. They come from sleep. He does this about 8 times a night. And he's now, that was when he was young. We recorded one night when he was 12 years old at the Children's Hospital, 72 seizures overnight. But he was not aware of all of them. So this guy that does this about 8 times a night, and now about once a week this occurs. And this disorder that came out of my PhD is called autosomal dominant nocturnal frontal lobe epilepsy. And it typically begins in mid-childhood at around 8 years and is characterised by clusters of nocturnal motor events. The patient may wake up and have an aura, which you'll miss if you don't ask them about it. And then they have events that can involve tonic stiffening. And the stiffening can be so severe that they can grasp onto their metal bedhead and bend it with the tonic contraction. Or they can have hyperkinetic attacks, such as the little girl I'll show you in a moment. The EEG is not very helpful, and because people have retained awareness often, they were misdiagnosed. Some thought were even diagnosed with hysteria because they thought they were putting them on. Now, we've got lots of PhD students in the audience, and if you do clinical research, you also have those assays that don't work, and you only get to hear about the ones that do. And so this is one that does. We started with 2 families, and 1 year of my life later, as a PhD student, we have this pedigree, 27 affected individuals over 6 generations. And it was with this pedigree that my molecular colleague, John Mulley and Ortrud Steinlein, could map it to chromosome 20. In those days, that took a year to map a family, and then to find the first epilepsy gene. Now, to everyone's surprise, it was a nicotinic receptor, and the mutation was right here at the ion channel gate. And this was the first evidence that epilepsy was due to ion channels, and opened the door, really, for it to be thought of as a channelopathy. And you're now well aware that there are cardiac channelopathies and many other sorts of channelopathies. So that's way back when, in 1995. If we fast forward to 2016, this can't have gone unnoticed. The precision medicine initiative of Obama, and really it's taking this approach, is worldwide. And this is based on finding a gene mutation and targeting that mutation and developing a therapy for a patient. So this is the same disease, but in a little 4-year-old girl, but from a family that when we studied them from a clinical research perspective, we said this is much more severe. This family has very severe psychiatric disorders with aggression and psychosis and intellectual disability. And indeed, this little girl was 4 here. She's now 16, and she's shown marked developmental regression, becoming non-verbal and stopping walking. So the same seizures, the same inheritance pattern, but a much more severe phenotype. So with our molecular colleagues, Sarah Heron in Adelaide, we performed exome sequencing in this girl's family. And she found a missense mutation in a sodium-gated potassium channel called KCNT1. And this same gene was found in the same edition of Nature Genetics. A French group implicated the same gene with de novo mutations in a profound epilepsy of infancy called migrating focal seizures of infancy. Interestingly, both groups then went on to show that the mutations cause gain of function. So you can see here the wild type or normal, and different mutations shown in blue in the autosomal dominant nocturnal frontal lobe epilepsy show a marked gain of function. Now, my colleague Steve Petru, who's a physiologist, together with Carol Milligan in his lab at the Florey, looked at this because Steve recognised that quinidine, which is related to quinine that you have in your gin and tonic every night. So quinidine actually works directly on this channel. And in their in vitro studies, they showed beautifully that it reversed the gain of function. So we've gone from clinical phenotype leading to discovery of a gene, leading to understanding mechanism, and now a potential treatment. So what does it do? Well, we're at early stages at this, but this is one very clear example. And in this migrating focal seizure phenotype, that's the profound epileptic encephalopathy, one group reported a child here, a girl of 25 months, who in vitro, the quinidine shows reversal of the gain of function, and in vivo in the little girl, her seizures improved and she made small developmental gains. And then we were fortunate to collaborate with a group from Duke who looked at 2 patients, one with a picture very similar to the girl I showed you, focal epilepsy and regression, some benefit in vitro, but no benefit in vivo. Yet in their second case, who had this very severe migrating focal seizure phenotype, they show some benefit, but not as much, interestingly, as this one in vitro, but 80% seizure reduction. So this is what precision medicine means. It means really using your biology to develop a targeted therapy. But we've got to get the outcomes right. And so this is a beginning, but we're by no means there. We need normal development and we need no seizures. And that's also a huge area for you to follow. So let's move on then to the severe infantile epilepsies, and there are many of those. But one that I've done much work in, and also one that is extremely well known, is called Dravet syndrome. And we also already heard from Ian about how you can put in a piece of a puzzle, and that can be incredibly important. And I like to use a puzzle to talk about this because these are very complex phenotypes and you have to put together all the pieces of the puzzle. One bit doesn't make the syndrome. So Dravet syndrome is where a child starts off completely normal, and then at 6 months of age, we've got oh, I know, I'm pressing the wrong thing. There you go. 6 months of age, a normal baby presents with an episode of status epilepticus, so a prolonged seizure, and that can involve jerking down one side or be on both sides. They then go on to develop additional seizure types, and here you see the photic stimulator flashing for that patient and triggering a cluster of myoclonic seizures. And you'll see, and if we had the volume on, which I'm sparing you, you'd hear he doesn't like it very much, but he's not going into a tonic-clonic seizure. So in Dravet syndrome, these children go on to develop other seizure types, focal seizures, absence, and often episodes of non-convulsive status, where they're just not with it for several days at a time or hours. Development's normal in the first year of life, absolutely normal, and then they slow and regress, and almost all have intellectual disability. They walk just a little late at 18 months, and we've shown in our older studies of older patients with orthopaedic surgeons and postdoctoral physiotherapists that they develop this very debilitating crouch gait. And so that's also something we need to think about, how we can make that improve. The EEG is normal, despite having lots of seizures in the first 2 years of life, but then it becomes quite abnormal with generalised and multifocal epileptiform activity. And finally, the genes. The gene here is known in most of the patients, and in more than 80%, they have mutations of the sodium channel alpha-1 subunit, and here you see the sodium channel embedded in the cell membrane. Here's the alpha-1 pore-forming subunit, and more than 80% of patients have mutations in this subunit. So by discovering this very complex phenotype, which Charlotte Dravet did, then people could go and look at the sodium channels, which first came to light because of work in febrile seizures and our finding of sodium channels in a milder febrile seizure phenotype. People then said, hey, febrile seizures are key to Dravet syndrome. And so they looked at that, and we now know that most of these patients are solved from a molecular point of view. So that's Dravet syndrome, and that's by way of background to the discussion about whooping cough vaccine and so-called vaccine encephalopathy. Now, this is from the London Times. It's not that long ago, 1993, and the victim of the whooping cough vaccine won a huge payout in those days for what that vaccine allegedly did to the child's brain. So what is vaccine encephalopathy? It's the sudden development of encephalopathy with seizures and developmental regression in a previously normal infant. Sounds familiar, doesn't it? And there's long been a claim of a causal link between the pertussis or whooping cough component of the triple antigen vaccination that has public health consequences, of course, with vaccine uptake and medico-legal implications. And despite this strong sense that maybe they're causing it, there are large-scale epidemiological studies that do not show that this is a true association. But if you're a parent and your child starts to seize within 48 hours of vaccination, it's very hard to convince you that it's not the vaccine that did it. So in our study, we were studying these severe epilepsies of infancy and childhood called the epileptic encephalopathies. And in those, we had a nested study of 14 cases which had alleged vaccine encephalopathy. Now, the eldest was 47 years old, so we went back and got their early history, and of course you can try and get the hospital records and you can ask the mothers and fathers, but usually the mothers in those days that would have lived through every seizure more closely. And we found that of those 14, 12 had a diagnosis of Dravet syndrome, 13 were associated with onset of triple antigen vaccine, and 11 had SCN1A mutations. So we showed that these individuals actually had a genetic cause rather than an immune response to the vaccine, and at the most, vaccines triggered a genetically determined disease. Now, the families had got their large payouts in the UK because they'd alleged that they had no family history of seizures, therefore it must have been the vaccine that did it. But the research showed us it was a de novo mutation, and therefore that's why there was no family history. And this obviously has societal and medico-legal consequences. We then took this another step, and we looked at our cases with Dravet syndrome and an SCN1A mutation, and we got the documents of the timing of their vaccination and the hospital documents for their first presentation. So we were eliminating recall bias, which of course is very important. And we examined the time between the timing of vaccination and seizure onset. So here's one of those source documents. Many of you will have a baby book just like this. This is Sam's son's baby book, and you can see here the beautifully stamped dates of their vaccine. You can see vaccination was very good for Sam's son. He's 6'6" and having a lovely wedding day here in 2007. And so what did we find? Well, we had 37 cases with SCN1A mutations and validated dates, and we had 24 that were vaccine distant, so their onset was not related to vaccination, and 13 that were vaccine proximate. And you can see here that within 2 days of vaccination, you can see a very clear peak. And that we then went on and examined those cases and said, are they any different clinically from the cases that were not vaccine related? And what we found is that they were exactly the same, they just started 7 weeks earlier. And of course, this leads to great fear for these families. What about the next vaccination? And so now we arrange for families to have vaccinations in the vaccination clinic at the Children's. And indeed, a 2-year-old I saw a couple of weeks ago was in the Children's for 24 hours and at 22 hours went into status. So it seems to be a very appropriate thing to do. We also talk about pre-medication with paracetamol. I don't think we know that that makes a difference. But the important issue here is that those children were destined to have Dravet syndrome, and if it wasn't vaccination at that time, the next stress, be it a fever or an illness, may have triggered it. So there's an example of how vaccine encephalopathy, we went on to find the cause, an SCN1A mutation. And then our colleagues, our basic science colleagues, have developed animal models showing very clearly that it's the inhibitory interneurons that are not working. And we have a very important role in dispelling the belief that the vaccine is causative. I don't think we've quite succeeded with that in our whole community, but you as medical professionals will have that important role. And if you haven't seen this, I would certainly recommend you watch it. You can download it from SBS. It's a beautiful movie documentary called Jabbed, and it's done by Sonia Pemberton, who's an Emmy Award-winning movie director, and she has showcased 6 different anti-vaccination stories here, and it's great watching to understand how all this vaccination debate has come about. So in my last few minutes, I just want to touch briefly on why be a clinician scientist and really echo some of the many messages that Ian shared. And some people would say, well, that's not what I signed up for. I wanted to be a medical doctor and I want to see patients, and why would I bother? That's going to be exciting enough for me. It's certainly what I thought as a medical student, having had no exposure to this world. I would put it to you, it makes my life and my work far more interesting. I have 3 careers all the time, often in a day, and by that I'll have a very busy clinic or an inpatient who's extremely complicated. I'll then go and teach, and then I'll write a paper with a member of my team, which is also great fun. But remember, clinical research is not basic science, and it's something you need a lot of skills to do, and it takes a long time to get there. So one of the messages is enjoy the journey. Don't worry too much about the end point, but enjoy each stage for what it is. Life is rich. We are extremely fortunate to have a career that is so exciting. Why bother? Well, it gives you a different way of looking at the world, and it helps you to make a difference far beyond the patients that you see, with a global impact, changing practice and changing outcomes. And I get to see that all the time, and I think it's really exciting. One of the things I think is worth remembering is that moment of discovery, that excitement when you realise you are the first person in the world to put 2 and 2 together, and that this can make a difference. And we can all do that, everyone in this room, but you have to get the right questions and the right time. So is it part of your day job? Well, as I said, you have to be a clinician to do clinical research. So 21 years it took me to submit my PhD and everything. I just wish someone had told me to stop worrying about the endpoint as much. So that's why I'm sharing that with you. And remember that every patient you see raises a new research question and can tell you something about the science. But you need to make sure you pick the questions worth answering. So are you trained for it? You finished med school, you're a junior doctor now or a fellow. You know, do you already know it all? Well, I would put it to you that the most you've got at the moment is a taste for research. You might have done 1 or 2 papers, a case series or something, but that's not real research. If you're really going to be a researcher, you have to do high-level training, and that is a PhD. It is a new career. You're not meant to know how to do it. That's what you're there for. And the most important thing is to choose a good mentor. And so I always tell my students, I expect every paper to have 20 drafts. My own often have 50. It is hard work, but you know, you can read them many years later and they still read well and give the message. So it takes time and dedication. But I think everyone here today is going to show you that it's very rewarding. It's not often you have glamour, as Ian shared with you, and I'm going to show for the women because you're worth it, and that's a L'Oreal catchphrase, but it just shows you this was my moment of very French glamour. And also, I'm very fortunate to have received the Prime Minister's Prize for Science with my colleague Sam Berkovic. Can't always pick your Prime Minister, but that's the way it is. And I'd like to finish by just showing you our fantastic team. None of this work can happen in isolation. This is one of our, we've had now 21 research retreats for epilepsy. We had our autism retreat yesterday, and we are just so privileged to work with bright young scientists, even bright old scientists that can help us to take it further forward. So thank you very much.
Thanks very much. It was a bit of a sea change from Ian getting more into the details of epilepsy, so hopefully the message around clinical science and taking the translation was clear. Does anyone have any questions?
Thank you for your talk. I wanted to ask about your relationship with basic science and clinical science, because you obviously have a really strong relationship with basic scientists and a very strong understanding of that. But as a clinical researcher, to what degree do you think you need training in basic science to be a successful clinician researcher?
Well, that's a fabulous question, thank you. I think there's no way I'm a basic scientist. I take blood really well still, you'll be pleased to know, all these years later, but that's about it. That's where I end, and I can't go into the lab. Completely the opposite of Ian, really. So I think it's really important that we meet and discuss. So our retreat is one example of that, but we have a halfway through the year retreat. We have monthly teleconferences with our molecular teams. We have weekly group lab meetings in which some of our molecular people are with us. So we're constantly talking. I have to say it still gives me fear and trepidation to put up some of the new molecular work when I'm teaching on a new topic, a new paper that's just come out, and I'll read it, and the physiology can be quite hard when you're learning. So you never feel across everything. I don't know if Ian would say differently to that, but I certainly don't, and the imaging. But that makes it so much richer because you're bringing in together so many pieces. And because we have very good relationships, we talk to each other. So if one of my molecular people or physiology collaborators get up and say something that's not right clinically, I'll come up to them afterwards and say, just think you need to say this a slightly different way, because it really does matter. And when you get up and if you say it wrongly. So I think it's all about communication and good collaboration. I can't be a basic scientist. The world is just, there's too much information, and I'm in a terribly small area, and I think all researchers these days are generally across a very small area of their research and have to be the world expert in their little bit of the world. So I think you shouldn't aim to do both. And my colleague and my closest collaborator, Sam Berkovic, when he came back from his time in Montreal, set up a lab. And after about a basic science lab with rat models, and after about a year or two, he gave up and said, you know, I want to do clinical research. And I think that needs more, you know, we need people out there to be growing clinical researchers, which is what part of what today is about. But today is about being a clinician scientist, so not just clinical research.
Other questions?
There were about 5.
Yeah, maybe over here.
There was some here.
Just building on what you talked about then about collaboration, you say that a lot of your research is built on what other people have done, and other people took your work and drew new conclusions. Is that something that is quite organic, or is that something that requires a lot of skills in networking and communication to be an effective collaborator and make sure you're not doubling up? Or
I think the answer is both, really. But I think the networking is important, the meeting with people, sitting in the same room, talking about the science. And one of the things I love best about our meetings is that we always get new ideas. And when I go to another meeting, I almost always come back with, hey, we should do this, and hey, we should do that. So it's about hearing people, but hearing people who are really at the top of their game and choosing your collaborators well. So you want people who are at the next step of the science along the way. And one of my molecular collaborators, Joseph Getz in Adelaide, he's always onto the latest bit. Heather Mefford, who's my closest collaborator in America, she's always on to the latest. She led the copy number variance study. But I came to her and said, I've got the population, the epileptic encephalopathies, can we look at that? And so it's about the talking together. And also very important about being generous. And we sort of, Ian touched on it, and I have a little bit. You've got to be generous and think very carefully about how you work with people in papers and things. It helps if you get on well, because that makes it a much more easy collaboration. Doesn't always work that way, but it helps if you do.
Hi, I'm Prof. Sheffer. Thanks so much for your talk. I'm really interested in how you've managed to juggle your work-life balance. So, you've had your own family, you're running your own lab, you're a clinician, you're a scientist, you're everything. How have you managed to do it all?
Thanks for that. I call myself an anti-role model, and that's because I don't think I juggle anything very well. I think you do work far too hard, so I don't think I have enough balance, and Ian has shown us the slopes, and I've been on the slopes for a long time. But I'm very fortunate. I've got a very good husband, and he's been fantastic and been very supportive. He's sick of award ceremonies though, so won't go to any of those anymore, so that's fine. But he's fantastic. So that's one thing, choose your partner well. Secondly, how do you do it? I think the thing that I miss out most is time for me, just to be honest about that. So how do I do that? I'm lucky because I travel a lot, and therefore I've found like-minded friends who are doing just the same as I am in other parts of the world. And one of my closest friends is at Great Ormond Street in London, and we would meet up every 2 or 3 months somewhere at a conference. So that's good. I have really great friends in Melbourne that I make an effort to see. But it is hard. It's a real juggle, but it's a very exciting life. And, here I am, how many years on? Far too many to count. And I, am excited to get up every day and go to work and see what I can do and see how we can change the world. So I think that's a real bonus.
Up the back there.
Thanks, Prof. Sheffer. I was wondering if you might be able to share with us some of the work that you're doing on medicinal cannabis. Has it been challenging to set up, and are the patients interested?
Yeah, look, I like to say it's ruining my life, cannabis, and that's because I have to press my cannabis button 6 times a day and tell people about cannabis. Because every patient asks about it, almost every patient asks about it. And so the trials have been a trial. So we announced in February that we were doing big trials from the States. By the time they got us drug, they'd closed the trial. So we were meant to have patients in for 10, 12 days, I think, for pharmacokinetic studies, and they filled it in the States, even though we kept saying we have the patients waiting, we're waiting for your drug to arrive. So very frustrating. Now we have started trials, but not in Dravet, in the focal epilepsies of adults at the Austin and around Australia. And there are numerous other trials being discussed. The Victorian government is growing its own, and so that's also a big issue. How is that going to be rolled out? And it's a very interesting and exciting time, but one where the science has been lost a bit with the media, and that's a real concern, a huge concern, because there's a whole lot of non-scientific, no evidence out there, and this case it worked, it was panacea for everything, and yet I know about all the patients who've sourced it or grown it and it hasn't worked. So we're getting a very uneven representation. The media is leading this, which is weird for us because we're used to lots of drug trials which are handled very appropriately. Nobody's interested except the patient and us, and suddenly the whole world's interested. So it is ruining my life, but I think it will make a difference. I think it will be as good as any of our other drugs in some of the epilepsies, but we need data. And that's a message that you as doctors need to be giving out. We need data. And that is coming. The first trials are really just being submitted now, but I think it will be part of our armamentarium, but it won't cure epilepsy.
Are there any more questions? There were a few hands up before that have timidly retreated. Okay, on that note, it's time for morning tea, so please one more round of applause for Ingrid.